Okay, good afternoon to everyone. It's a great pleasure today to have, it's a great pleasure and honor to have this interview with John Hennesy and David Patterson. They are two ACM Alan Turing Prize winners. They are two leaders in computer science and engineering that have shared their knowledge in books that have become liminal in any curricula around the world. I would like to say that the length of the curriculum vitae is inversely proportional to the importance of the person, and the limit in this case is when you just mention the name and that represents the whole trajectory of that person. There are very few computer scientists in that club, and for certain, today we have the opportunity to talk to two of them. I'm not going to get into details. I invite especially the students to do a short search on both of them, and you probably will become overwhelmed. Professor Hennesy and Professor Patterson have written the liminal book about computer architectures that we use to teach in every university. But their influence is far more important. They were the leaders of the reduced instruction set computers, RISC, that in the mid-80s challenged the well-established complex instruction set computers. At that point, a large debate was started and probably still continues between RISC and CISC processors. Today, the market share is for RISC processors is over 70%, and perhaps even more. CISC processors are using RISC technology today. This gives an idea of the impact of the ideas of Hennesy and Patterson. But their influence is even much larger. Professor Hennesy has led Stanford University for more than 10 years, in which there was a sustainable growth. Professor Patterson was University of California, Berkeley. He was president of ACM and created a new processor, the RISC-V, that is open source and is being used worldwide in several areas as it can be developed in free ASIC chips. Now, having introduced to you our guest, I would like to follow a historical view, and I'm going to let Julian to make the first question.
Okay, thank you. And again, it's a great pleasure to have you both here. So I wanted to start off with a question about your background, as both of you developed your careers in California, in the in Silicon Valley area. So what do you think that are the main differences between those times, like the late 70s, beginning of the 80s, with what's going on today in Silicon Valley, with some companies even leaving?
You want to start, Dave?
Just going to say that to you. All right. It was I think the kind of the amazing thing for those of us who've been in the field for all this time is every few years we say, wow, it's really going even faster than it was just a little while ago. And we would say that again with this current era of AI. It's amazing how fast things are changing and what it's able to do. So But I noticed I was going through, I had to switch offices, so I went through a lot of old papers. And I said something almost exactly like that word for word in 1980. Or no, 1990. I said that almost exactly word for word. Wow, people don't understand how fast things are changing. So it's been exciting, and it's been fortunate for both of us to be in Silicon Valley. But it's it's the center of the computing universe at a time when computing is having greater impact on the world every year.
Yeah, I think we've been fortunate to see lots of revolutions in technology, right? The microprocessor, the personal computer, the internet, social media, the World Wide Web. But I think, as Dave said, the AI revolution is both faster moving and broader than any of these earlier ones. I mean, you see this rate of adoption. More people have used chatbots, AI chatbots, in a relatively short period than used cell phones over 5 years after they were created. So we're seeing very quick adoption of the technology and demand for this technology that is simply unprecedented.
Thank you for your answer. It must have been wonderful to be there at those times. Being a computer scientist or engineer in the 80s with the Moore's law running very fast was probably a race against time. I can imagine an era in which large mainframes computers were changed by mini computers, and suddenly the microprocessor produced a complete turnover, making the personal computer the new standard. But to swim against the current must have been difficult. How do you come to the idea of a RISC architecture? Was to overcome the limits in the Moore's law and the CISC architecture? What was behind that wonderful idea of regular instructions, all with the same structure, a very few to be very fast executed?
Well, I guess we're going to alternate. There was a lot of topics there. I do remember teaching a class. I think if you believed in Moore's law, you believed that microprocessors, which were kind of toys in the 1970s, they would be in microwaves or in actual toys. They weren't seen as real computers. But I think John and I believed in Moore's law, and if you're going to double transistors every year or two, eventually that was going to dominate. But I think I remember teaching a graduate class of computer architecture in the 1980s at a time when the VAX mini computer, which was like at the size of a refrigerator or a few refrigerators, was the main computing engine for the department. And I said that in the future, computers like that will be too slow because they're so big. And the graduate students laughed. They thought I was making a joke about it. So this, so then I guess, trying to introduce RISC, I think the question was whether the instruction sets of these mini computers, these large computers, made sense for microprocessors or not, if microprocessors were going to win. And I think that's what led to RISC. John, are you still there?
Yeah.
Okay.
My
Camera.
video disappeared. My camera disappeared. I'm still here.
Okay.
So, there's another thread here. Both Dave and I had worked on technology, compilers, and software technology for microcoding. So we both understood microcoding, which of course was what all the microprocessors were using. They were all microcoded engines, right? And the instruction sets, as Dave said, copied largely from mini computers. And we said, well, why not just make that microcode instruction set kind of the instruction set you compile to, and then eliminate the process of interpretation at hardware time that all these machines were doing. So it was from the very beginning, the RISC ideas were driven by efficiency and how to get efficiency in the use of silicon. How to get, while we weren't so worried about power at that time, that turned out efficiency in the use of power turned out to be a good side effect, which became crucial when we went to lots of small devices that were handheld and battery powered and things like that. So there was this other common thread, I think, that that we shared in when we were doing our work.
Okay, thank you so much. So now, well, now RISC is pretty much everywhere, and well, I see that originally they were developed for efficiency and competing with the CISC, with the complex instruction set at the time. So so now they are in mobile devices, peripherals, communication infrastructure everywhere. But what do you think is the future of RISC? I mean, it's so commonplace now, but there's also this new trend for open source hardware that has gained space. And maybe the future is also even in RISC-V. Do you see that moving forward?
Yeah, I'd say RISC right now, the RISC architecture ideas are really just about everywhere. Cloud computing, Amazon has an ARM-based servers. Google in its cloud computing has ARM-based servers, and so there's probably the kind of the classic mainframes for business data processing doesn't use RISC. Maybe, I mean, there's not many places that you don't see RISC architectures today. So I think it's a lot more than 70% of it. The RISC-V effort that was led by my colleagues at Berkeley, Krista Sanovich, and graduate students, it's this kind of exciting idea that we could have a common architecture that humanity could use. So we would compete on the implementations, but we could have something that is compatible software from the tiniest thing to the biggest thing, so that the people who are involved in RISC-V community are kind of inspired by that vision that we could have a lingua franca, a common instruction set everywhere, and it would be free and open, not belonging to anybody. So that's what motivates that. I think, there's what's happening, what's interesting is happening, when John and I got the Turing Award, we said the next decade, and I guess we said it about a decade ago, was going to be a golden era for computer architecture because of domain-specific architectures. And I think that's held up pretty well. But what's happening very recently is these agentic systems, where you're having AI do a bunch of work for you. And it turns out when AI is doing a bunch of work from you, you're running standard tools, things that you want to do, like compilers and other CAD tools and stuff like that. So in agentic systems, suddenly the CPUs are where all the time's been spent, whereas maybe just like 3 or 4 years ago, all the time was being spent on the GPUs or the TPUs that were used to create these large language models. But now that it's being applied in agentic systems, suddenly the bottleneck is the speed of the CPU again. So I would say where it looked like almost all of the investment wasn't in the CPU a few years ago, going forward, it's a rebalancing of that, and we're going to have to figure out either how to make CPUs faster or to make the tools that run on CPUs a lot faster. So tag.
Yeah, so I think those are good comments. I mean, things have shifted in the last 10 or 15, even 20 years, where the major limitation for designers is power. Energy becomes the major limitation, and that's what you're balancing. And of course, that depends a lot on efficiency of the underlying implementation. It's why DSAs were so much better than any conventional general purpose CPU. They're much more efficient at doing those things. I think Dave's right. We're in this agentic era is really taking off, which is going to put more weight on the CPU, but it's also going to put more weight on on the interconnects and communication technologies between the CPUs and multiple GPUs. So, which is a place we're going to need further innovation if we're going to speed up and get more advanced machines. But the opportunity that these machines could bring for doing scientific research, for really solving some of the really difficult problems that the human race faces is really incredible. And I think we're going to see, we already saw last week, a bunch of Stanford researchers reported discovering 16 new viruses using AI as a search tool. But lots of conventional CPUs as well involved in doing that. So I think it'll be an interesting era yet again.
Well, thank you very much for your answer, and you certainly answer more than one question. You go further in
Well,
the line.
we're professors, so you know.
Exactly.
Once you get us started talking, it's hard to get us to stop.
Yeah.
Nice professors for sure. So let me ask the people in listening to this interview if they want to make a question. So perhaps you can come here and ask the question, because we have the microphone on the desk. So come on.
I see a hand.
Yes, yes, come on. He's a student, so
He looks like one anyway.
he looks like
Yeah.
one.
He dresses like a student.
Hello, how are you? Thank you for being here and giving us the opportunity to ask a question. My question was that as silicon approaches physical and energy efficiency limits, could biological substrate offer a viable path toward more energy efficient computation, or would the overhead of interfacing biology with silicon eliminate their potential advantages? Thank you.
Do you have thoughts on that, John?
Did you get that?
Yeah. I think biology operates in a very different way than electronic systems currently operate, and they don't mix too well together. You're exactly right. That's a complex interaction to get them to mix together. If you look at the efficiency of the human brain in terms of 30 watts. I mean, and you look at what it can do compared to electronic systems, it's truly amazing. On the other hand, it takes advantage of certain structures that we can't easily replicate in an electronic environment, like almost unlimited fan out and fan in with very large degrees of 3D structure, right? Which is not what electronics looks like, unfortunately. So what we ought to be thinking about is, are there things we can learn from the structure of the human brain and how it operates to improve the way we're building these new AI-based systems, right? Which currently don't, they have a very primitive model of neural networks, but it's extremely primitive, much more primitive than the human brain is. So we should be looking for inspiration from neuroscience to ask, could we structure our electronic systems differently to take advantage of some of the things that obviously our human brains take advantage of? And that's an open research question, but a very important one, I think.
Great answer.
Anyone else?
Any other questions?
Come on.
We'll go.
Sorry. I wanted to ask, thank you for being here, first of all. And I wanted to ask, going forward with how agentic AI is transforming development, do you think it will be more or less worth it to know the ins and outs of computer architecture, and for a worker on the microcontroller space to completely and fully understand the basis of how computers work, how memory works, how a linker file works, everything very low level, how assembly code works, that sort of thing. Would it be more or less worth the effort to learn these concepts?
All right, I'll take a shot and let John react. I think the challenge going forward for people in school is to become expert at something. And if you're going to be in computing, become expert in computing. At least right now, these amazing agentic systems, from like a faculty perspective, they're like really wonderful grad students, very smart, but they're inexperienced. Energetic, very smart, and so you can kind of launch an army of them to do stuff, but they make mistakes all the time, and you need to be there to guide them and tell them that's a mistake and not. And if you're experienced and you have, if you have that expertise and can recognize when they're making mistakes and correct them, you can make amazing progress. But also, if you don't, you can make, the phrase AI slop. You can generate a lot of code chock full of bugs and security holes and and things like that. So that, I think the challenge going forward is, how do you become experienced? How do you become expert? And how do you know? I mean, right now when I use these tools, they'll make up lies all over the place. There's nothing that they know. So there's nothing I can count on that they won't make a mistake on because it's so obvious. So my guess is you do need to have that breadth of knowledge, so that in case the question, in case the thing that you wanted to build touches on some of those things. But I guess the difference is now you won't be doing it yourself. You'll need to learn that stuff, but it'll be like being a professor or a researcher. You'll have these assistants that you're guiding. So I don't know exactly how that would change your education, but I think, as far as I can tell, I think you still need to become an expert on all those topics. What do you think, John?
Yeah, I agree with Dave's point. I think, there's two different reasons for learning about some of the basics of how computers operate. First of all, if you're a computer scientist or you're a person who works in the computing field, having some understanding of what's going on in the underlying hardware affects how you think about things. I mean, if you write software, but you don't understand how memory hierarchies and memory systems work, you're going to write very inefficient software. So there are things like that you have to have a good instinct that I think of them as kind of foundational. Everybody who's in the field should understand certain things. Obviously, computer science has expanded to the level where you can't be an expert on every part of the field anymore. When Dave and I were both young, you could go to virtually any PhD oral and understand what was going on. But today that's impossible in computer science. You couldn't listen to PhD exams or job talks and really understand what's going on because the field has gotten so big. So everybody then has to have something where they're, as Dave said, a deep expert, where you really have real expertise. And then you have to learn how to work with other people in a team, because now the number of people that work on building a major computer system is phenomenal. So you've got to figure out, okay, where's my level of expertise and how do I work with the rest of the people on the team who are going to be doing either the lower level stuff or the higher level stuff in the stack. So you've got to make that work, and I think that's critical to real success.
Do you think agent systems any thoughts of how agent systems will change that? Because your team's now going to, I assume, will be a mixture of people in AI agents.
It certainly will. It certainly will. And I think you alluded to the real problem, Dave, which is that these things sometimes, they don't have any problem producing something that's wrong.
Yeah.
And they don't always know it, that they produce something that's wrong. They're trying to please you. So they'll give you something that's wrong rather than say, oh, I don't know how to do this. It would be better if they occasionally said, I don't know how to do this. I need some help here. But that's
It'd be a lot better.
Yeah, it would be better.
I even, they'll even defend to the death when they're wrong.
Yeah,
It's, you know,
they have.
or when
They have.
they're facts. Yeah,
They
there's a
have.
fact they're wrong, and they I've seen them refuse to admit it. So,
Yeah. They've gotten better over time, but I still remember once I was writing something for a colleague who happened to go to graduate school at Yale, and it threw in this statement about that I was writing about him, that he was born in New York City. And I said, why was he born in New York City? He goes, well, that's where most people who go to Yale are born. No, okay, wrong.
Okay. Other questions? Do I call on you? Yeah, come on. Whoever wants to come first. So do you have the mic? Do you have the microphone?
We're too intimidating, Dave.
Okay. Well, I wouldn't want to ask questions in Portuguese.
Sorry, we were muted.
Okay.
Yeah, I can't hear.
Oh, sorry. We mute
Here now.
the microphone. Sorry.
Well,
Okay.
we weren't trying to stop you, just rest assured.
Listen to your ears. Okay. What areas do you consider important to continue promoting in order to preserve diversity and the capacity for innovation in computer architecture?
What was the first word?
I mean,
Areas.
areas.
What areas? What areas?
Memory, storage memory, cache, pipelines. What areas are important in computer architecture in the future?
Boy, I guess, are there ones that are important now that aren't going to be in the future? Well, that's tough. I mean, right now, for example, a lot of these AI systems are memory bound. You know, we spend there's a lot of innovation in making very high performance processors and do amazing number of teraflops, petaflops of operations, but they're often limited in practice by the memory system. And then in the beginning when they were single chip systems, you know, like you do inference on just one chip. But nowadays they're ganging, you know, dozens of them together or scores of them together to do inference as well as training.
Mm-hmm.
So there was what was John, like processor memory switch? That was this kind of classic categorization of the components of the computer. It's hard for me to see a piece that isn't important. Storage. I mean, people are talking about, using the jargon, the key value cache for the large language models. People are talking about putting them in the storage system. And these days, given the slowing of Moore's law, packaging is really important because you're trying to put a lot of chips together in a small system. So, maybe John can think of something.
No. Those are all good. Those are all good. I mean, right now we have HBM, which is a kind of 2.5D, but going to real 3D or going to something that gets much denser to get the connection shorter is going to be critical, I think. As our memory systems have become absolutely crucial. In fact, despite the fact that large inference problems as well as training problems have lots of computation that needs to be done. They're memory bound. They're not generally bound by that computation, even though there's a lot of it because they can quantize it and do other things to make it very efficient. That part is energy efficient, and we get lots of computation done. So memory systems become, which means interconnect, because memory systems are inherently interconnect bound. And now as we go to larger collections of chips to do inference problems, especially with long context. Long context is driving a big part of this, because if I want to use an agentic system to do kind of a scientific research, the first thing I'm going to do is feed in the most important 500 scientific papers on the field. So now I've got giant context for this thing, and that's a key, particularly stressing the memory system. Stresses both the entire system, but the memory system in particular. And we're kind of near the end of the road for DRAMs. DRAMs have been improving very slowly in the last. Latency hasn't improved in more than a decade, and bandwidth's improving, but very slowly. And it's longer and longer between generations. So that just is going to mean additional challenges for the computer architects in terms of using their memory systems efficiently.
You can even see the importance of memory in the stock market and the commodity prices. That kind of shockingly for John and I, the price, because we have these plots that go over all 7 editions of the books showing the price of DRAM dropping. DRAM went up by a factor of 4. Mm-hmm. It went up, and it's probably going to stay there. And it's just supply and demand. They can't make enough chips to match the supply and the memory system. And then the companies that can make this high bandwidth memory and deliver it, they're having huge profitability. So as profitable as NVIDIA is, these memory component vendors are making historic profits, and that's kind of the capitalist system reflecting the value of its technological pieces. So yeah, I'm sorry, you can't skip anything in our book. You got to read all the chapters. There must be something, but even floating point arithmetic. There's a huge amount of innovation in floating point arithmetic, which you'd think it'd be, that was settled with the IEEE floating point standard, but 4-bit and 2-bit floating point arithmetic. It's shocking that these things work. So they're kind of innovating everywhere in the stack in this quest of more performance at lower energy costs. And plus, kind of, since Moore's law is basically gone, now the way we're getting more performance is a lot more chips. So packaging now plays this really giant role. So yeah, it's and
I think it's, when we did the RISC work, we were kind of operating across the compiler instruction set boundary, kind of working on just that one boundary. But it was pretty straightforward. We didn't really look very far up the stack to say, well, what were Fortran or C programs doing? We looked really at the compiler interface. Nowadays, you look at how many levels people are going up and down the design stack to do, and they're thinking about packaging and fundamental technologies, and they're thinking about what the domain-specific programming model is and what kinds of applications are being used and how are they being used. Because depending on how you organize your system, a big inference system, for example, a system that's designed, say, on my phone, where I want a very interactive kind of response environment, I'm not batching up a lot of stuff, versus, let's say, a big data center that's doing a lot of agentic thing where you can run large batches of things through your system. The architecture is completely different for those two systems. So I think we're going to see a lot more interaction between the application stack and the architecture going forward.
Okay. Another question from people in the room? Yes. Come here.
Well, first of all, thank you for your time and for being here. My question is related to RISC-V CPUs. In the last few years, we have started to see RISC-V CPUs on the market, some even competing against traditional desktop PCs. Do you believe we are starting to see the last of Intel and CISC CPUs?
What was that? Can you repeat the last sentence, the last question?
Do you believe we are starting to see the last of Intel CPUs?
Oh, the last of Intel CPUs.
It's pretty hard to. That'll be pretty hard to kill.
It'll take
I
a
think-
long time to go away.
The PC market, John and I think when the RISC days started, at least I thought people would distribute software at source code and then people would compile it. That is not what happened. What happened is people distributed kind of for sensible reasons. They distributed it as binaries. So it's wedded to the instruction set. So the PC industry is largely defined by the x86 instruction set. Now, Apple broke away from that and they used the ARM architecture. So that piece of the personal computer market is using ARM, but there's probably still hundreds of millions of PCs sold a year that are basically defined by the x86 architecture. So I think the numbers will decline, but boy, I don't, when does it go to zero? Right? I don't think John and I will see that day.
Yeah. I mean, compatibility will be there for a long, long time to come, even if the sales begin to dwindle over time, and they have to some extent. I mean, certainly a lot more phones sold than anything else, right? And so that's really changed the dynamic. But Dave's right. I mean, instructions. It turned out instruction set compatibility object code compatibility became critical in the shrink wrap era, and it didn't go away. It became more important. So that's gonna give a very long tail, and we'll see what Intel does over time.
I think we'll see. I think what's happening with the exciting new products, right? And the exciting new products probably aren't going to be x86 based. So if the growth is in exciting new products rather than in the existing products, for some reason that the PCs would come back. Like I suppose with agentic systems, PCs could come back. So is that what's going to happen, or x86 is going to return to glory in agentic systems because of using these old tools, or will they use RISC architectures in these agentic systems? That'll be kind of interesting to watch.
Thank you for your answer. Another question from the room?
Big chance.
Thank you.
I had a different question from before. I was wondering, you spoke a lot about Moore's law and how hardware improves over time dramatically, but I think we've also seen the opposite happen with software, where there's a common joke where software people undo all of the advances of hardware people. Where
that's a hardware designer's perspective.
Yeah.
We're making these wonderful computers, and the software people just screw them up. But go ahead, finish your question.
I mean, because over the last 20 years, pretty much everything on a personal computer nowadays runs JavaScript or a similar interpreted language and abuses the resources that improving hardware has given us. Do you expect something similar to happen with embedded devices, where we now have ESP chips with megabytes of RAM and a lot of processing power and multiple CPUs, and this applies to other microcontroller families as well? Do you expect interpreted languages to arrive to microcontrollers and the embedded space, and sort of the same thing that happens in personal computers, where everything runs an interpreted language and takes up way more RAM than it should? Is that a trend that you see happening, especially as more junior people don't want to learn C and stick to interpreted languages like Python or JavaScript, or MicroPython in the case of microcontrollers? That's the question.
Do you have an opinion on that, John?
Well, I think it's probably the case that if software costs are significant and they can be reduced by use of interpretive higher level languages, and the hardware you can afford the cost of the hardware, then I think it's a good deal. What made that possible was that hardware got so cheap, right? It kept getting faster and faster, so you could afford to do it. But I remember many years ago, I was talking to probably the last living computer pioneer, Maurice Wilkes. He was the last person alive who had worked on the very earliest machines, the ENIAC and the EDSAC and machines like that. And I asked him, I said, Maurice, what's going to happen if hardware stops getting faster at the rate it's been getting faster? He said, then programmers will have to be a lot more careful about the code and the efficiency of code they write. And he's right. If that happens, we will either the programmers will have to be, or what I suspect will actually happen is AI-based compiler technology will figure out how to do that, bridge that gap much more efficiently than we do as programmers.
That was the one comment I was going to make is I've talked to a couple of, I am not a programmer, but I've talked to a couple of programmers, and like I said, their view is they've got this army of smart but inexperienced grad students writing code for them. It's easy for me to imagine some kind of prototype in Python, and then what you do is tell one of your graduate students to go rewrite that in C++, and they don't complain, right? They'll just do it, and if you say, oh, that didn't, you messed up there, they'll just start over again and do it again. So I could imagine this kind of rewriting of software for efficiency in special environments is just it's going to be one of the tools. Right now, what happens with AI systems, which is kind of shocking, a test of how good they're at coding, the test is rewrite the Linux kernel, which is in C, in the Rust programming language. That's a test. Imagine how much, what a phenomenal task that would be for a human being to rewrite the Linux kernel in another programming language. But that's kind of what they're doing. So I could imagine that there's always been this argument for, why aren't we using computers to make programmers more productive, right? And so I can imagine prototyping in Python. I think that's what most beginning computer science students are learning Python these days, right? So I think I wouldn't be surprised if that's where it starts, but that might not be where it ends up.
Mm-hmm.
I may ask another question. We have here in this conference a special track for quantum computers. And this is becoming each year more popular, and people are starting to do research and teach quantum computers and the curricula and so on. So what do you think about that line of computer science?
You have a view, John?
Well, I think quantum, we still there are still a bunch of big hurdles that the quantum computing community is going to have to do. They're going to have to get much larger number of qubits, or dramatically improve stability of qubits in order to make something practical. The current stability and the cost of error correction is just too high right now. So, and that's gonna limit their use. The other thing is it's really important to have critical algorithms of problems you really want to solve that are going to work on what I would call medium-term quantum computers. Let's say the quantum computers we get over the next 5 to 10 years. What algorithms do you want to? Everybody's running the same thing. They're running some cryptographic cracker, right? I mean, and that's not going to support an entire industry. But I think the work on quantum is vitally important because the problems that they are trying to solve, stability, sensing, things like this will be critical as you get near the very end of the life of silicon, the last 10 or 20 years of silicon. Those are things that are going to be critical in silicon systems because the number of errors you get in silicon will go up very slowly. Right now, the number of errors you get in silicon compared to quantum is lower by, 10 to 15 orders of magnitude. But as silicon gets more and closer to thermodynamic limits, then the error rates in silicon will go up. And we'll have to figure out some of the techniques that we use for quantum in silicon as well. So there's important work on the basic physics, which will be useful in any event going forward.
So I've actually got a meeting that I have to go to in 5 minutes, so I need to give a 5-minute warning.
Yeah,
I've got a hard stop.
Thank you. So do I did.
I know we are over the time, so I'm just going to ask the people in the room if they have another question. Wait, I mean, no. Come on, here. That's one more.
Sprint.
Yes. Hello. Hi. Thank you for being here. So John, you answered recently that everyone should manage like the basics and everyone should understand it, like a couple of questions ago. And I want to know what you guys consider the basics. What is something that everyone should manage?
Well, I think everybody who's a computer scientist should be able to say, okay, here's a line of code in C or Python or anything you want. Here's how that line of code gets changed into eventually into electrical signals and the computer works. I think understanding that entire stack as a foundation, it's not something you're going to use every day, but it's a foundation that's really important. So I think that's still important. You don't need to be an expert. When I went to school, you took an entire course on assembly language programming. You do not need an entire course on assembly language programming. You need to do a little bit once so you understand how the machine is actually working. But I think understanding that stack, it's one of the remarkable things about computing is that we go from these gigantic software programs of incredible complexity and ability down to individual gates changing what they're doing, and understanding that entire stack is how computing really works, and it's magic at each level. So I think that's a fun and remarkable thing to learn.
Yeah, I remember I think in the 1980s I had a guest lecture from a guy at a mini computer company come, and maybe it was a graduate course, and they asked him what do you recommend to know, and he said almost the thing John said word for word, is to be able to look at a program and understand everything that happens between you when you hit the button, like what happens in the keyboard and the signals and the interrupts and the operating system. Because if you don't understand that whole round trip, you'll have these holes in your knowledge, and then at some point those holes will kind of lead you astray. But just being able to see, like, when you hit a key in the keyboard, what happens at all levels of the computer system. If you gain that knowledge, you'll have great intuition in a lot of situations. But it was kind of, so 40 years apart, that same advice holds, I guess.
Still works.
Still works. Pretty useful stuff.
Yeah.
Okay. I would like to thank you, both of you, for being here. As I said at the beginning, it's a great pleasure. And I would like to make the point here. I wrote to these incredible two professors 4 months ago, asking them for this interview, and they answered yes. They answered yes. So it's great. you see so many people with so little background being like, oh, I'm so great, but the big people.
We're not so great, I guess.
Yeah, you are. The really good ones are happy to come to this national conference in Argentina, just in a Zoom meeting, and share with us your points of view. And of course, we are very, very happy with this interview.
I enjoyed it.
I'd like to say thank you, and it was very, very interesting and very, very nice to see even both of you. I mean, it's also meaningful to see you both answering questions and interacting between yourselves, and we are very grateful for this.
Next year, when I teach my computer architecture course, I'm going to say I took on hire with these two incredible guys. So please.
All right. Bye-bye.
Muchas gracias. Hasta la vista.
Hello? Yeah. Oh, sorry. Yeah.
Bueno,